So, ladies and gentlemen, we'll start the meeting of Columbus Astronomical Society for September 2024. Okay. So, I guess we'll start with. Yeah.
How's it going, gang? I appreciate Dick Moore, is he here? I don't see him. Sending me a lovely article, and James Luke sending me a lovely picture for the newsletter. That was very, very helpful. The newsletter belongs to you guys, so if you have anything that you are interested in sharing with the club, whether it's very low-level beginner stuff like I had a really great vacation and I stood on top of a mountain and it looked great, or this is what my PhD is on, anywhere in that realm, feel free to send it my way. It's primefocus@columbusastronomy.org, and I will put it in the newsletter. I do very much appreciate all the submissions. John Glenn Astronomy Park is still in operation. We are doing our programs on clear Fridays and Saturdays. If you haven't heard that, we are going, our season goes all the way to the week before Thanksgiving, and then we take a break for the winter period. I'm thinking of maybe having a couple spontaneous Mars programs in January of 25, because that's around Mars opposition. In case you guys aren't aware of this, the planet Mars, when it goes around the sun on the outside track around the Earth, actually takes 26 months to come back around again and be on the opposite side of the sun from the Earth. And that 26 months will actually, the next time it will happen will be in January of 2025. And Mars will be at its best and brightest for this particular go-around. This particular go-around, however, Mars is at aphelion, which basically means that it is at its furthest point from the sun. And that means that Mars will be particularly far away this time around, and it will be very small. It's only going to be 14 arc seconds, if that means anything to you. 14 arc seconds is significantly less than the maximum size it can be, which is around 25 arc seconds. So it's a good 60% normal size. So it's going to be a dinky little thing, but it's still opposition. It's still going to be nice and bright and relatively big at that time of year. So I'm probably going to do a few programs in January to accompany that. And I also just want to kind of tell you about something that was coming up. That's all I have. Charles, you want to take it over? Okay.
Okay, so Isaac.
Well, greetings, everyone. My name is Isaac Cruz, and welcome to everyone that is here. I'm the lead for CASIS. CASIS stands for Columbus Astronomical Society Imaging Special Interest Group. So the key words being imaging. If you're interested in actually taking images of the sky, things that are actually up there, and have ever kind of thought about taking a camera or a telescope, and maybe the combination of camera and your telescope to take pictures of what is out there. Next Saturday, we'll have a meeting for CASIS at 1 p.m. in the afternoon, right here on this same venue. And it's basically open to all the members, to anyone that actually wants to come that day. And again, if you have any questions, or if you're interested, if you're ever being interested on it and you have kind of questions about how to actually do it and what do you need to actually do, I invite you to come to the meeting. I'll be here all night and more than happy to answer questions that you may have. Again, next Saturday, 1 p.m. right here. Thank you very much.
Okay, next we have Joe Stark here, our outreach coordinator.
And I'm also the greeter. We have some guests here for the first time. Charisma and Jordan, they're sitting in the back there. Anything you'd like to say about yourselves? To introduce yourself? You may or may not, it's your choice.
I'm trying to get into the astrophotography, so I figured that I'm just learning the basics.
Okay.
This is my son.
Jordan, do you want to say anything, or just?
Pretty much the same as
Okay.
trying to learn the basics of photography.
Great. Welcome. Welcome to Columbus Astronomical Society. The other thing is my outreach coordinator. We have two events coming up in October. I cannot make either one because I have previous commitments on both of those Saturdays. One is on October 12th, and the other one is October 19th. They're successive Saturdays. And one is in Canal Winchester, the other one is at Glacier Ridge. Basically what they want from us is just to tell people at an area that they give us what we do, what our club does, where we meet, the times that we meet, some of the activities that we do. You can have a telescope there on display if you want. Obviously, you won't be able to use the telescope. It's going to be daytime. But they're in the day, one is from 11 to 3, and the other is from noon to 4. I have some sign-up sheets that I'm going to pass around. If you at all can make it and would be willing to help us out, please put your name and telephone number on there. If we don't get anybody for the 12th or the 19th, then we won't be able to do it because I'm not available on both of those Saturdays. So, any questions about that? Basically, they just want us to introduce the club and tell people what it is that we do, okay? And where we meet, those kinds of things. All right, thank you.
Okay, and now we want to hear from our host.
Yes, hi, I'm Don Stevens. I'm the director here at Perkins Observatory. And I want to tell you about our Friday nights. Most Friday nights, we do public programs where we have the public come. And if it's a nice night, we show them things through telescopes. If not, I'll tell them about stuff up in the sky, give them a tour of the observatory. But we're always looking for volunteers to help out with the programs, things just like parking and running a telescope. And you don't need to be an expert to run a telescope out there. Sometimes we'll have experienced observers out there as well, and usually we'll pair you up with somebody and they can help you start to learn stuff in the sky. So it's a good way to start to learn the sky as well as kind of one of the programs. So if you're interested, the programs start at 8 p.m., doors open at 7, volunteers usually show up around 6:30 or 7 o'clock to get set up. And so we'd be happy to have you. Again, you don't need to be an expert or anything like that. Not going to make you get up here and give a talk or anything like that or a tour. Just help with the parking or show stuff through telescope for folks. All right.
So, one last thing before our guest speaker. We need to get 3 members for the elections committee. It's annual elections coming up in December, and we need 3 members for the nominating committee. And if anybody is interested in running for one of the offices, now's the time to think about that too. So you can see me after our speaker if you want to volunteer for that, and we'll go from there. So would you introduce our guest speaker?
So our guest speaker for the evening is Professor Christopher Kochanek. Am I pronouncing your name correctly? He is from...
It's supposed to be Kochanek, but the family gave up on that.
Kochanek, okay. I will attempt. It is Professor Christopher Kochanek, okay, and I am Brad Hoene. He is from Ohio State University, and he's given talks for the New Vistas series of lectures many times. So if you've been to the New Vistas in the past, he's done a number of those. So thank you so much for coming, and I appreciate it. Let me get you set up with the microphone, and we will get you started. So this should probably just go on your lapel there, and then just put this in your pocket. Appreciate it, thank you.
All right. So how many people have looked at one of these things? A supernova remnant?
In Class A?
Yeah. So this particular one is Class A. And I started playing with something, and what I didn't really realize going into it was that figuring out how far away these things were is a bit of a mess. And for what I wanted to do, I needed to know how far away they are. But it's an expanding blob of gas. So how do you figure out how far away an expanding blob of gas is? So I'm going to tell you a bunch of different ways. So what are they? Well, they're remnants of exploding stars. Exploding stars come in two flavors. They're what are called the core collapse supernovae, which are the deaths of massive stars, so things about 8 times the mass of the sun and up. They will explode and leave behind neutron stars or black holes. The other one are the thermonuclear supernovae, and those are explosions of white dwarfs. So basically you have a white dwarf made of carbon and oxygen, you push it over instability, you flash burn it all to iron, and the thing explodes and there's nothing left over. Okay, so these ones will always leave something behind, these ones will leave nothing behind. Okay, but they will both produce remnants. All right, well, what is the remnant? Well, when you set off that explosion, you release the amount of energy which is about equivalent to what the sun does over its entire lifetime, except you do it in a few milliseconds. And then you eject a lot of mass. Well, in the case of the white dwarfs, you eject about 1 times the mass of our sun. For the massive star ones, it can be 10 times the mass of our sun. That goes all flying out at initially like 10,000 kilometers per second, and then slows down steadily. But then it sweeps into the interstellar medium surrounding where the star exploded and sweeps up that material. Well, when it sweeps it up, it also has to accelerate it up to the velocity of the other stuff. And in order to do that, you end up with what's called a shock wave. The shock wave heats all of the gas. If you make gas toasty hot, it likes to radiate in various ways. And so the supernova remnant is, what you're seeing in your images of the supernova remnant are the emission from these shock waves because of the collision of the fast-moving material with the surrounding gas. And so you can see them in optical, X-ray, radio emission, and that thing which you can see is is the supernova remnant. They sort of light up for real after about a century, and then they can stay lit up for some tens of thousands of years. And then basically, as time passes, they just go slower and slower and slower and just kind of fade out. Okay. So here are a bunch of them. Here is the youngest one. Technically, it's not really a supernova remnant yet, but this is supernova 1987A. And so what you're seeing is where the shock wave is intersecting a wind structure that was surrounding the star. And then just going through the other recent ones, this is Class A again, probably around 1680, but it's not clear whether anyone saw it. Okay. Kepler, so Class A was a core collapse supernova, so a massive star. Kepler was a white dwarf explosion, 1604. It's about 20 light years across now. The question mark is because it suffers from this question I'm asking is its distance is not really known. And if you don't know the distance, you don't know how to turn this into a size. Tycho was the next one. It's about 45 light years across. It was also a thermonuclear explosion. The Crab Nebula was 1054. It was a core collapse. And then if we go to some older ones, this one's not showing up very well with the light, but this one of the nearest ones is Vela, which is only a couple hundred parsecs away. Okay, that's sort of 10,000 years old. And here's another one which just pop up a few times. It may not mean anything. The remnant is called W50. It contains an accreting black hole called SS433, and it has this very non-circular shape. But there's several hundred supernova remnants known in our galaxy. What are they used? Well, if you can look at them closely enough, you can try to work out the energetics of supernova, how much energy the explosion put out, how much mass it ejected, which is interesting. In X-rays, you can try to work out the composition of the ejecta, how much iron was put out, how much oxygen. They are a source of a lot of cosmic rays. which is interesting. They're the locations of the youngest neutron stars, because by definition, the Cas A neutron star is 500 years old. And when neutron stars are that young, you can actually see them cooling off in the X-rays, which probes interesting physics about the properties of neutron stars. The game that got me into this is I was interested in what are the binary properties of the star which exploded. So what we come to is the star our sun is not normal, right? Most stars are in binary star systems, not singlets. And the presence of a binary has a lot to do with how stars can evolve and various other things. So, okay. So for the thermonuclear ones, they all have to be binaries. That in order for the star to explode, something has to be adding mass to it to push it over to the point it will be unstable and explode. Okay? So all of the thermonuclear ones are in binaries when they explode. The question is, who is the binary companion? And so for 50 years, maybe even a little more, I've been arguing about whether the companion is a normal star or a second white dwarf. And so one way of addressing this question is you go to a thermonuclear supernova remnant and you see if you can find this guy. Right? It would still be close to the center of the remnant. It actually should be somewhat more luminous than it was, because in the normal model, your poor innocent star is basically sitting epsilon away from the thing which explodes, and so it gets walloped. In fact, the star actually gets put out. Is that the shock wave goes through, the shock wave for the explosion goes through the normal star, actually causes it to expand enough that the nuclear reactions at the center turn off for a while. It's the only way I know of to put out a star. For the core collapse ones, the binary things are much more complicated, because first, they don't actually have to be binaries. But in fact, an even bigger fraction of massive stars are in binaries or even higher order systems, triples or quadruples than stars like the sun. People have surveyed, if you look at them before they explode, or younger stars, it's just doing a survey of what the binary properties are, and then you can estimate what might happen. And so the estimates are that basically only 1/3 evolve like they're actually a single star. 25% of them, you start out with 2 stars, and before it explodes, they merge to make 1 star, and then the 1 star explodes. 33%, when they puff up to be a red giant, the binary companion will remove the envelope of the star. And another 14% will do more complicated interactions with transfer of mass between the stars and so forth. But we're also very interested in going from this to how many binaries do we end up with after the explosion, because the binaries you end up with after the explosion are many very interesting systems. You have accreting systems, so where the star is still there, it's dumping mass onto what is now a neutron star or a black hole, and you get X-ray binaries and things. People are very interested in binary pulsars. There's remain a good test of, say, general relativity, but now you have to figure out how to start out with 2 normal stars, end up with 2 neutron stars in orbit around one another, and what's the chance of that happening? And of course, these things are also going to be the progenitors of what we now see as gravitational wave sources, because the gravitational wave sources are either a neutron star, a neutron star, a neutron star, and a black hole, or a black hole and a black hole merging, and all of those had to go through a phase where not one of the stars, but both of the stars exploded, and they would have been in a supernova remnant. So one way we can ask how all this statistics works is, okay, we sort of know the statistics of there being binaries at birth, but if you go and look in supernova remnants, you can try to work out the statistics of there being binaries at death. And you can, in fact, look for surviving binaries. You can look for binaries which became unbound. You can, in fact, look for whether they were in triples and whether the triples are unbound and so forth. So you can do statistics of the binarity of stars at the time of death rather than at the time of birth. So that was the project that I was interested in. So what are you looking for? I mean, you're looking for a star which is basically in the middle of the supernova remnant. Right? That, in general, the supernova remnant is expanding much faster than any orbital velocity of the star. Okay? So the star is moving relative to where the explosion happened, but slow compared to the expansion of the supernova remnant, so it's got to be somewhere close to the center. All right? If life was easy, you would just know everyone's distances, and you just say, that's the star that's near the center of the supernova remnant. But you can't do that well. Basically, is most stars don't have distances measured as accurately as the size of a supernova remnant. But basically, for the stars we're interested in, we pretty much know their distances now. Right? That we have this semi-miraculous Gaia satellite, which measures the distances to stars. And so now you just say, query database, give me the distances to all the stars in the direction of Cassiopeia A, and there you have it. Okay? Okay, but that doesn't help me if I don't know where the ball of gas is. Okay? So this is going to be various ways you might try to find the distance to a ball of gas. What I hadn't fully realized as I got into this is just how awful the situation was. The distances to most of these balls of gas are known to factors of 50% or 100 or factors of 2. Okay? The one which is most common is that most supernova remnants are radio sources. Okay? And so if you have a radio source and then you put some cold hydrogen gas in front of it, the radio emission that overlaps the SETI line, the 1420 megahertz line of hydrogen, will produce an absorption feature in the radio spectrum. And so you can measure the velocity of those absorption features. Okay? If you think some of that gas is very close to the blob you're interested in, it can't actually be the blob you're interested in, then it gives you an estimate of how fast gas near the explosion was orbiting the galaxy. You can then use a model for how things orbit in the galaxy to try to turn that into a distance. Okay? There are lots of problems. Since you aren't actually getting the velocity of the gas which exploded, right? You are getting velocities of gas in front of the blob. You have no guarantee that the velocity you're getting is that close to the blob. And then this method only works in some directions. It basically only works for things towards the center of the galaxy, not towards the other direction from the galaxy. And then it has a bunch of other issues, and hence this usual uncertainties of factors of 50%. Okay, direct parallax. So here is this W50 remnant again. In radio, you'll notice a bright point source in the middle. Okay, that is an accreting black hole, okay, called SS433. It is also there in the optical. Since it is in the optical, it is basically a star observed by Gaia. Right? Gaia sees the star that's dumping the material onto the black hole, and you can get a parallax. If you're not into parallaxes, the game is basically here's the sun, here's the Earth's orbit. In the ideal geometry, you measure the angle to this guy in whatever, June. Then you wait 6 months, and you measure the angle to the guy at, what have I gotten to? November, I guess, if I did June. And depending on the distance, right, this angle becomes smaller and smaller and smaller as the thing gets further and further away, and steeper and steeper and steeper as it gets closer. And so basically the parallax is you measure this angle. And in fact, the whole origin of the unit of parallax, which is what we astronomers use rather than light years or something, is a parallax of 1 second of arc corresponds to something which is at 1 parsec. So something is 1 parsec away, this angle will be 1 second of arc. This is, of course, why none of these were measured until the 1870, because even the nearest stars we know of are further away than 1 parsec. And so people had to get pretty good at measuring angles before they could measure one. And the advantage of Gaia is Gaia can measure this angle down at the level of a few tens of micro arc seconds. And so Gaia will give you a 10% distance at a kiloparsec, so 3,000 light years will get you a 10% distance, which is very impressive. Anyway, so this one has a parallax of 0.12 plus or minus 0.02 thousandths of an arcsecond. And so that gives a distance of about 8,000 parsecs. SS433 is a fun object. It has a radio jet, and the radio jet precesses. So I'm spinning sort of around my head. The jet comes off at an angle of 23 or 24 degrees, and then it twists around like this. And so projected on the sky, that corkscrew shows up looking like this. Okay? And so as it goes out, the jet is twirling around, and so you see projected on the sky as a corkscrew. It is a radio jet, so you can also use VLBI, and you can actually watch blobs moving along the jet. The velocity is 0.26 of the speed of light, neither a little more nor a little less. And people have modeled the kinematics of this and say that gives a distance of 5,500 parsecs, which doesn't agree with the Gaia distance. So I pointed this out to the person who had written this paper. She was still pretty convinced she was right, but anyway, no one has tried to figure out the origins of this little discrepancy. Well, it's possible that there are issues with Gaia. This is getting small enough that you have to start worrying about some systematic effects in Gaia. So if it still persists in the next Gaia data release, I would say they have to be wrong. But I would say there's still some room for it coming out right. This is a one-off. This system is practically unique. All right, here's another fun one you can only do for a few things. We have this stuff between the stars called dust. Think soot particles. The dust not only absorbs light, but it also scatters light. And so if we are sitting here and the supernova goes off here, we will see direct light from the supernova. But if here's a layer of dust, the light can also go up to the dust, scatter off of it, and then come to us. And so we will see light from the supernova sitting off to the side here. You can measure this distance. Okay? And you also have what the time is since the supernova. So you know the supernova happened here. This path is longer than that path, so you see this sometime after the supernova. There's a delay. It turns out if you measure those two things, you can get this distance, the distance of the supernova from the dust layer. Okay? Doesn't give you the distance to the supernova because you don't know the distance to the dust. Okay? And it doesn't tell you anything about that distance. All right, here are some examples of dust echoes, just so you can see them. Here are the dust echoes from supernova 1987A. They have this interesting feature that if you have a lot of dust, it seems like the dust knows where the supernova is. Right? This is V838 Mon, which is not a supernova. It was a merger of two stars. And you can sort of see this shell around it. And it's not that it actually knows anything about it. Right? The echoes are actually physically far, far away from the actual event. It's just a property of the geometry of the system that it wants to look like a bunch of circles expanding around the target. Here are some dust echoes from our Assassin project. We weren't the first to find them, but we actually found better ones. So this is a dust echo in Cassiopeia A. Okay? And so what we do is we take a whole bunch of images from 1 year, add them together, take a whole bunch of images from a couple years later, subtract the two. As time passes, the echo these expand outwards. Okay? And so when you do that, what you see is a plus-minus signature where the echo has moved. So all of this along here is an echo from the Cas A supernova, seen 400 years later. And here's another equivalent one from Tycho. So these are quite far from the actual supernova. So this schematic shows you where they are. You can see that each of these traces is where they are from year to year. So they steadily are moving to the left. And the Cas A supernova was almost 8 degrees off this way. So these are quite a ways away from where the supernova occurred. Well, they have to be quite a ways away because you have to have a path length which is 400 years longer. Right? So it has to be, you have to have quite a long angle. Here's the same. We don't get quite as nice ones for Tycho, but you can see them moving away, and center of Tycho is 6 degrees up to the upper left. Okay. Gaia provides the trick for solving this problem. So we didn't do this, but lots of people have taken Gaia. You have the distances to a whole bunch of stars. You take the stars and estimate the amount of dust in front of each star. And so now in any particular direction, you have a whole bunch of stars at a range of distances where you know the amount of dust per star. And so you can make a map of where the dust is in distance. Okay? And you can use that to work out this. And so I get this from the echo. I get this from these three-dimensional maps of where the dust is. And so I can measure d plus d, which is the distance, big D plus little d, which will give you the distance to the remnant. And so you can do this for Cas A, where we confirm previous distance estimates. And for Tycho, we actually get the first good distance estimate for Tycho. And in the department of binaries, it rules out everyone's favorite candidates for possibly surviving stars from the explosion of Tycho. They are all at the wrong distance. So bringing it back to the question of binaries. All right. So far we've got 3 things which are not super generic. We've got getting a direct parallax, which I forgot to mention, but was on there. There are 2, which are done with radio pulsars. Okay, and there are 4 which you can do because there's an accreting binary system from the leftover remnant. So the explosion left behind an accreting system, and you can get a parallax to the star, which is providing the stuff to dump onto the neutron star or black hole. Okay, so one is, SS433 is the one black hole, and then there are 3 accreting neutron star systems. So that's a grand total of 6. Remember I said there are hundreds of these? We're not making much progress. SS433 is again, the one system. And as far as we know at present, those are the only 2 you can do with the dust echoes. Okay? You can't do the dust echoes for things which are super old. Basically, the surface brightness of those echoes gets steadily fainter the further away they go. And they're already pretty low surface brightness. And the other thing is the dust has to be in the right place. So in theory, you might try to do this for the crab. But if you look at the distribution of dust towards the crab, the echoes, if the crab is that way, the echoes would be kind of over here, like almost 90 degrees away is the geometry of where the dust is. So in theory, if the explosion's there, you can actually look for the dust echo behind you. In theory, you can get an echo that goes past you and then comes back. But as you go further and further away in angle, they become harder and harder to find. So that combination of they both have to be pretty young to be bright enough to find, and you have to have the right dust geometry means this is a pretty niche application, but it's fun. Oops. All right, this one's a little more generic. So I've got an expanding supernova remnant, and I can try to measure how fast it is expanding 2 ways. So in particular, much of the optical, well, all of the optical emission you get from a supernova is from emission lines of atoms. So if you look at a supernova remnant, or if you take an astrophotography picture of a remnant, in the red emission of the supernova remnant is mainly an emission line of hydrogen. Okay? But because it's emission lines, you can measure Doppler shifts. And so if I take a spectrum of the supernova remnant, the Doppler shifts are the velocity of expansion towards me. And so in theory, I can measure this velocity, the velocity parallel to the direction I'm going. All right, if I'm a patient man, all right, I take a picture of my supernova remnant. I come back in, pick your number, 10 years. I take another picture of the supernova remnant. Okay, and the supernova remnant is expanding, so my second picture of the supernova remnant will be bigger than in the first picture. And if I can measure that, I can measure how fast it is expanding in the plane of the sky. Okay? And how fast is that expansion? Well, that expansion you can measure is the velocity of expansion this way divided by the distance. Okay? So I have 2 things. I have this thing, which is a velocity divided by the distance. I have this thing, which is just a velocity. And if you do some extremely complicated mathematics, if you take this and divide it by that, right, you will get that it is the distance times the ratios of the velocities. And if you make a bold leap of faith, that velocity is the same as that velocity, and you have the distance. Okay?
It's assuming the explosion is spherical.
Yes. Okay. Here are some examples. This one is visual. This is a little piece of the edge of the crab explosion. And so here is a ground-based image from 1998. Here is a Hubble image from 2006. And this is the direction of the supernova expansion, and you can see it shifted across. And so people have done this. There's mainly a guy at Dartmouth who's done a lot of this. And so here's some supernova whose name I didn't even write down because it's got some Einstein X-ray detection name, which isn't going to mean anything. Doesn't mean anything to me either. But basically he's done this. He's gone in. He's been doing this for decades. Take a picture. Come back many years later, look at the differences, and then all of these arrows are where he thinks he can measure an expansion velocity. You can see he gets pretty good coverage around it. And this actually also gives you a way of measuring, trying to estimate the age, right? Because if you know how fast this is expanding and you know how big it is, you can try to estimate how long ago the explosion happened. Life is not so simple because the expansion velocity is not a constant. It's decelerating, it's slowing down with time. But okay, he's got a velocity, and so it all works. As mentioned, one is how much you're going to trust that one velocity is equal to the other. Obviously the issue is in fact, this is not a sphere, then this velocity has to be different from that velocity, and well, this is not a sphere. This one's a little extreme, okay? It is possible that those jets, this is SS433 again, the jets coming off of this guy go this way and this way. And so some of the morphology of this one may be driven by the jets shoving it out. But there's no reason to trust this to, it might be reasonable to trust it to 20 or 30%. So maybe this gives you distances which are safe at the 20, 30% level, but it's very hard to do any check of what it is. And the other problem is you just have to wait, right? Most of the supernova remnants you look at are fairly old, because by definition, there's a lot more time to be old than there is to be young, okay? They tend to be further away than 1,000 parsecs, and so they're expanding not super fast anymore, and they're fairly distant. To give you a scale, if I go 1,000 kilometers per second for 1 year, and I'm at 1,000 parsecs, the motion per year is 0.2 of an arc second. Okay. So typically when this guy Thorstensen is doing that, he's using baselines of a decade to make these measurements. So it is not a route to distances with instant gratification. All right. So this is where we came up with, or stole, some combination of a new trick for doing this. Really is I noticed a paper from almost 30 years ago, which played this trick but in a very inefficient way. And so our real realization was just that you could do this much more efficiently. So here's some spectra of two stars. This is a hot blue star, and this is a cool red giant. Okay. We have the gas between the stars, and the gas between the stars contains lots of things. And amongst the things it contains is calcium and sodium. Calcium and sodium are interesting things because they have some absorption line wavelengths which are super strong. So they're not the most abundant elements, but they really like to suck up certain photons. Okay? And so here is a little chunk of the spectrum of the blue star near an absorption line of calcium, an absorption line of sodium, and this big divot taken out at the center of each is absorption by all of the interstellar medium between us and the star. Okay. And you can see it's pretty easy to see. Okay. Here's a cool red star. This one here, again, is the interstellar medium, but you can see there are a whole bunch of other notches taken out of it. Okay. The problem is cool stars have lots and lots of absorption features in the stellar atmosphere. And so most of what you're seeing here is the star, not anything happening from absorption. The other thing is calcium is actually fairly far out in the blue. Cool stars really aren't very excited about putting many photons out in the blue, so it's fairly faint, and you can see it becomes really ratty because there aren't many photons. So if you want to go looking for absorption, you want to look at these hot blue stars because A, the stellar atmosphere doesn't have any absorption features. Okay? But basically, in particular, calcium and sodium would be fully ionized in these atmospheres, and so they can't do calcium and sodium absorption. And then also, you can do the calcium pretty easily because now they're blue stars and have lots of blue photons. Okay, well, that's the interstellar medium, but I have all of these other features, and if you just believe what I said, is those can't be from the star, so something else is producing a bunch of higher velocity absorption features in the spectrum of this star. Right? Doesn't matter whether it's plus or minus, but interstellar medium, the velocities are predicted to be very low. Okay? And here's something at about 90 kilometers per second offset. Here's another 90 kilometers per second one way, 90 kilometers per second the other way. Okay? Ignore this. That's actually, this guy comes in a pair, so this is one of the pair, and that one on the edge is the other one of the pair. Okay? And if you're careful, you can actually identify them, but basically, the easiest thing to do is just toss these guys out for now. So we'll just do hot blue stars. So where am I getting high velocity absorption features from these stars? And the thing that people have pointed out at various times is it can be absorption features from the supernova remnant. So basically, the supernova remnant, you have a ball of expanding gas, right? It is moving fast compared to the motions of the interstellar medium. And so if you put a star behind it, you can see absorption features at very high velocities. Okay? They're not super high velocities because if you take J-random supernova remnant, it's pretty old and so no longer expanding super fast. But it's expanding faster than the typical motions of the interstellar medium. Okay? So I've sort of said this. So these guys are the interstellar medium. Okay? Those guys are all coming from the supernova remnant. Okay, so here's...
Question about that. Presumably, the supernova remnant's quite large, and there's going to be multiple stars behind it. Can you get better signal noise by sampling many, many stars, and then you're actually kind of averaging out the spectral lines in the atmospheres?
It's coming, it's coming. Well, for the red stars, what you have to do is model each star. Because we have good models of what the atmospheres of these stars do, and so you could try to model where all the stellar features would be to find the other ones. It's just a lot more work. Is one of my colleagues got from his advisor, his advisor is called Paczynski, the Paczynski diagram, is when you're doing science, there's easy, hard, interesting, and uninteresting. You should always try to work in the easy, interesting corner. And never work in the uninteresting, hard corner. So doing the red stars would be interesting but hard. So, okay, it's not a major sin, but start with the red blue stars. But yeah, that's essentially the game. We have Gaia, and so it's basically like the game the other people were playing with building these dust maps. We have a whole bunch of stars where we know the distance, right? The ones in front can't show absorption features from the supernova remnant, so they should only show the typical things from the interstellar medium. The ones behind, will show the interstellar medium, and then they may show a feature from the supernova remnant. Okay, one thing we have to figure out is what defines, what is may, okay, how much of that. And so that's the game, okay? So we did this one. That's a pretty big supernova remnant. So each of these circles is 1 degree across. So this supernova remnant is quite big. And what we do is our riff on making this efficient is the paper that inspired this did 70 stars one at a time, which is a lot of work. We use this thing. It's a robotic spectrograph on the 6.5 meter MMT telescope. And so each of these things coming in can be positioned robotically, and each of those is a little optical fiber pickoff. And so we can get spectra of 240 stars at a time. Okay? In fact, we have more fibers than we have good stars. This is a hydrogen emission line image of the supernova remnants. We did these 3 pointings, and all of the colored things are stars where we found high velocity absorption features. The ones where we didn't aren't shown on there. Okay. All right, so here they are in the space of basically distance. Okay, we actually did it. The units are actually the parallax, because that's what's actually measured. But these are the close stars. Those are distant stars. Red is sodium absorption. Black is calcium absorption. And so you're going out, and basically, aside from a little few exceptions, you don't see much high velocity. And then you get to about here, and then suddenly there's an explosion of high velocity lines. One reason we picked this system is this is one of the 2 with a parallax distance to a pulsar. And so the parallax distance to the pulsar is this band. And so you can see is basically right when you hit the range of distances consistent with the pulsar, suddenly you see this splash of high velocity absorption features. Okay. And one of the reasons for doing this is this helps as a proof of principle that you get the distance which people think they have. So here's the final result. You do some fancy statistics, but this is distance. This is actually the probability distribution you would get for the distance given the pulsar. It's not super well measured. This is the red curve is what we get from analyzing the appearance of the high velocity absorption features. So it's many times better than the parallax. And the other reason this is cute is this is the one supernova remnant known in the galaxy which seems to have a star that was unbound in the supernova explosion. Okay? And that star has this distance, because it's a star, so it's in Gaia. It has a Gaia distance, and you can see it's smack in the middle of what we got from the absorption features. This looks quite promising. The other thing you can do is you can ask, if you ask who has high velocity absorption and who doesn't, you can correlate that with where the H-alpha hydrogen emission line emission is. Okay? And so this shows the distribution of emission line intensity, okay, and just sorted by number. And so these are the guys with high velocity absorption. These are the guys without high velocity absorption. And so basically it's saying is that if you are on top of a region with emission line emission, you are more likely to find high velocity absorption. So it actually even gives you a way to try to target better, is that if you're trying to choose which stars to observe and you happen to have one of these images, you want to pick the stars that are on top of the black and not the stars which are in between the black, which could make this even more efficient. So people bought this. So we're in the process of doing this for about 10 more systems. And basically it should work for any of these blobs of gas where the stars are bright enough. And the main thing that kills the brightness is a lot of galactic supernova are behind a lot of dust. Okay? And so you absorb out the light. That would be the reason to eventually knuckle down and do the red stars, right? Because, of course, the blue light is more killed by dust than the red light. And so for the ones with a lot of dust, you may have to knuckle down and figure out what to do with the red stars so you can use the redder bands. But it's, in theory, super efficient, right? Is if you have one of these multi-object fiber spectrographs, in theory, you could do 1 or 2 pointings. The exposure times we're using are like an hour. And so you get a distance to any supernova remnant where the stars are sufficiently bright in an hour or 2. which certainly beats waiting a decade, I think. And so, maybe a little too soon to call it revolutionary, but it does provide a fairly clean way to efficiently get distances to blobs of gas. So, and that was my little story.
On the stars that get thwacked by the explosion, companions, he said that they expand and then it shuts off the nuclear fusion process. Do the stars collapse back down and reignite, or?
Yeah, they'll reignite. So I don't think you.
Helmholtz time scale, or?
I don't remember this. The external appearance is that actually they will become brighter, sometimes significantly brighter for like a century or a millennium. And that's basically just that the surface layers have been puffed up. And so then the surface layers will cool, and as they cool, that makes the star more luminous. So they can be like 100 times more luminous than the original star for a little while. I mean, that's one argument against also any of these candidate stars in Tycho being one of these things, because they're not anomalously luminous. But yeah, the other signature is you also blow off some of the surface layers of the star, and that you can look for spectroscopically. But basically, it's a bit of a long-running religious war, but I would say that it's pretty clearly that it's the white dwarf channel and not the companion normal star channel. But now I'll have to watch my back driving home.
Not quite that smart, but what is the purpose of all of this? I mean, it's fascinating, and you're seeing stuff in deep space, and you're measuring stuff that was never measured by the Galileos and the people in the BC and all this kind of stuff. I mean, does the government use this kind of stuff?
No.
Research? For research?
Mostly. We learn a lot about, people are interested in the history of the universe and all of these things. People certainly are interested in what we do. Do we save the world? No. Most of our students, fair number end up doing something related to astronomy, but a fair amount of them leave the field. They have no trouble getting jobs. So these days, the data science people snap them up. So the students never have any trouble. But
the data that you get from Gaia, is that daily? Is it?
So the way the Gaia satellite works is basically they do data releases every year or two. So basically the satellite sits up there and is continuously scanning. So they're continuously collecting the data, but then every few years they do an analysis of all the data they've got and put it out there. So the next release is supposed to be middle of next year or something.
So live to 25, will it just disintegrate or swing back around?
No, exactly what ends spacecraft, depends on what's going on. I don't remember exactly what's limiting with Gaia, but it's usually eventually something breaks. Usually if a satellite goes up and starts working, it will work a really long time. Okay. The other thing is satellites may need consumables. So, for example, the Webb telescope lifetime is ultimately limited that in order to stay where it is, it needs some fuel, and eventually it will run out of fuel. So that can end it. And then depending on the orbit, you have orbital decay, and eventually the orbit decays. So if Hubble does not break for other reasons, its orbit does decay, and so eventually it would re-enter. But
following on that, with each release, do the error bars go down from the Gaia data, so you get a slightly better signal?
Yeah. So the distances, at this point will only slowly get better. The big thing that is supposed to be the next release is an enormous expansion in the number of binary star solutions. So the Gaia can also look for binary stars by two routes. One is it does measure Doppler shifts, and so you can measure it by the classic binary velocity. But the astrometry solution can also include the back and forth wobble on the sky due to it being in a binary. And so those solutions will also get. So in the current data release, there are something like 100,000 binaries, and I think in the next one it's supposed to be more like 1 million. So, but yeah. Anyone else?
Are you looking to build a model of supernova expansion to ultimately, I mean, to get enough of these, you'll have a rough idea of what a type 1A supernova will do over its lifetime?
Well, one of the problems of not knowing the distances is you can't do the energetics and the mass loss unless you know the distance, because the distance comes in. If you're doing this expansion in the plane of the sky to get the expansion rate, the actual velocity then is proportional to the distance. So that means that then the mass is proportional to the size cubed, right? And so the energy is dependent on some crazy power of the distance. Okay, so just even not getting the energetics of the supernova remnant straight, you need to know the distance pretty well. So it helps for that. My technical interest in this was I was curious about this game of what are the binary properties of the stars at death. So, but it enables other people's games as well. So, yeah.
Of all places, I saw something on YouTube claiming that Betelgeuse is going to boom. Is that a bunch of hooey, or can you predict such a thing?
So there was a kerfuffle a couple of years ago that Betelgeuse did a sort of had a unusually large dip in brightness. Betelgeuse goes up and down in brightness, and this one was just a little bit bigger, and then it just came back up again. And in fact, people were getting images of it during this, and you could actually just see is that basically there was just sort of a big dust puff came off of it and made it unusually faint. We don't know of any clear signature of how close you are to explosion. Certainly not on the long time scales. There are claims, which I don't really agree with, that at least some of these things will do something weird in like the last, call it, decade. But anyway, it's a long story, but I don't really believe it. But because we have this project where we take images of nearby galaxies, and so one of the things we have is images of the stars before they explode. And so one of the things we thought would be it'd be really cool if they do something weird just before they explode. We could we call them circles of death. But so far, at least in our data, we don't see anything that would let us draw circles of death. But who knows? Maybe the other people are right. We will see.
But for 1A, like tau coronavirus, right?
Yeah, for 1A, there'd be no. Yeah, it's only the core collapse where people are arguing about whether there might be some precursor signal, but they're talking about precursors on the scale of years, not. Okay. Anyone else? All right.